So now it's 2 minutes past 2. I'm going to now pass it to Dr. Hemmingson. Feel free, Sherry, to start your presentation. Thank you.
Thanks. Let me get my screen shared here. Sorry, I'm trying to get the proper screen showing. There we go. Okay, great. Well, thank you, Carlos, and thanks everyone for joining us this afternoon. I'm really excited to be able to talk to you all today about fluorescence theory and how to get great data. First, I think it'll be beneficial to just take a quick look at JASCO Corporation, the Japanese spectroscopy company. JASCO started back in 1958 with a Nobel laureate infrared spectroscopist and is located in Hachiochi, Tokyo. Our North American and South American offices are here in Easton, Maryland, and JASCO has been producing exceptional spectroscopic and chromatographic instrumentation, a full range of instruments. Many of you may be familiar with these, but today I'm going to focus on fluorescence. And JASCO's been doing that a long time, with the first system being introduced back in 1967. So I'm excited to share with you fluorescence theory, sample solution, and quantitative considerations, instrument design and components and data collection, as well as close out with some practical pointers for optimizing fluorescence signal. Luminescence is all around us, right? Whether it's kids' toys or adults. If you're into OLEDs, faux LEDs, or QLEDs, display technology, black light water slides, luminol detection of blood, or just the most beautiful displays in nature like algal blooms in this phosphorescent bay, and many other more lab-based applications you may be familiar with, like fluorescent imaging, fluorescence resonance energy transfer, thermal melts, or fluorescent ELISA is very applicable today with COVID-19 detection. The list goes on, right? Biochemical, environmental, material science, food science, and I'm sure you can list a few sitting there yourself of applications that are important to you. So today what we want to look at is luminescence and the fundamentals. So let's break it down. Luminescence can be defined as photoluminescence, which is fluorescence or phosphorescence, chemiluminescence, which is observed as bioluminescence in nature, and other examples like sonoluminescence and electroluminescence. If we're going to understand luminescence, we need to first understand how molecules get rid of excess energy, and that can be radiant or non-radiant energy loss. In radiative deactivation, molecules lose energy as a photon of light, and this is luminescence. But there are competing processes, and non-radiative deactivation is always there. It's the loss of energy without a photon, usually as heat or some kind of molecular motion. Now, in terms of the types of emission processes, there's basically the three that we looked at: photoluminescence, which includes fluorescence and phosphorescence. Fluorescence being on more of a nanosecond time frame, phosphorescence much longer lived in the millisecond to hundreds of seconds and even longer. And an excitation light source is required for this, right? We have to get light into the system. Chemiluminescence, on the other hand, excitation is by a chemical reaction. So even in bioluminescence, no external light is required, the chemical reaction produces this energy which excites the molecule. Now, every spectroscopist likes to show the Jablonski diagram, so I'm going to. You've all seen it in general chemistry and other, higher level classes you've taken. We have a ground state and a singlet excited state. There are, in any molecule, we have lots of vibrational levels. And so in the blue, we can see the absorption process where the molecule is excited from the ground state to the first singlet excited state. Again, there's lots of vibrational levels to excite to, so tends to be very broad. Over here, we can see if the molecule does not just relax non-radiatively, but takes that absorbed light and maybe loses some in the form of heat here to get to this first level of the first excited state, then it has the ability to decay by giving off photons to any of these levels, vibrational levels, in the ground state, and this is fluorescence, okay? Now, there are other processes, right? So if there's intersystem crossing, that means basically that the singlet excited state and triplet excited state have really good overlap of these energy levels. Then the molecule can transition to this triplet state, lose some energy vibrationally down to this first level of this excited triplet state, and then can give off photons down to these vibrational levels of the ground state in the form of phosphorescence. However, if these levels don't have adequate overlap, then we don't see phosphorescence, and fluorescence would be the dominant emissive process. Now, and that's true, right? Lots of things absorb, fewer things fluoresce, and even fewer things phosphoresce. But let's take a look. How do molecules phosphoresce and what's involved with that? Well, we need to take a look at the spin states. So again, kind of going back to really general chemistry, right? If I have electrons in the same orbital, they have paired spins. They have opposite spins. And in fluorescence, when the molecule is excited to this singlet state, even though the electron's excited, the spins stay paired. However, for it to be a triplet state, notice the molecule has unpaired electrons in this. So for it to transfer from the singlet state to the triplet state through this intersystem crossing, this electron has to flip spin. So that's one barrier, right? And then to relax back down to the ground state, it has to flip again because no two electrons in the same orbital can have the same spin, right? So phosphorescence is known as a spin-forbidden process. And you can even see just with these steps here why it would be a longer-lived process as well. So if all things fall into place and we have the right molecular structures that allow for the overlap of these singlet and triplet states, and we can radiatively decay to the ground state, then we get phosphorescence. So now that we understand kind of the physical chemistry of it, what kinds of substances fluoresce? Well, highly conjugated organic systems with many alternating single-double bonds, any aromatic species, and rigid planar molecules, right? That's going to minimize how the molecule can move around, right? Minimize the modes of deactivation. So a few examples. Highly conjugated system here, you might recognize it. It's not vitamin A, it's beta carotene. Highly conjugated, very fluorescent, actually a great chromophore as well. And no aromaticity, right? So just a really highly conjugated network. My biochemists in the room should be liking these molecules: tyrosine, tryptophan, and phenylalanine. These are the 3 aromatic amino acids, which are awesome because they provide intrinsic fluorescent probes for studying protein interactions. So a great way to not have to perturb your protein with extrinsic probes, but use these intrinsic species to tag interactions. Rigid planar molecules, there's a huge list of these, and we like to call this the molecular chicken wire crew, right? So we get these fused aromatic ring systems and polycyclic aromatic hydrocarbons, or PAHs. These are all highly fluorescent, and the degree of the extent of this network really allows for a pi cloud of electrons above and below that molecular network, so that we get a great deal of delocalization, and it really promotes that and stabilizes that pi to pi star transition that we need for fluorescence to occur. So now it's your turn, all right? Hope you've been paying attention. Which molecule do you think fluoresces more? All right? I hope you quickly caught on to this link here, right? This carbon bridge locks these two phenyl rings into place and definitely allows this to have a better structure for fluorescence, right? Promotes that rigidity and planarity. If you look at the names, it's kind of a giveaway, biphenyl versus fluorine. So how do we determine how well a molecule fluoresces, right? We can quantitate that, and that's called the quantum yield or quantum efficiency. We can look at the number of photons emitted as fluorescence ratioed to the number of photons absorbed by the molecule, and that's going to give us a value in the range of 0 to 1, and numbers then approaching 1 are going to be great fluorophores, right? So if it's 0.9 and we have 100 photons that are absorbed, we'll have 90 photons emitted as fluorescence. So we ideally would like to choose probes that have high quantum efficiencies, and the probe designers and the chemical companies really work to achieve that as one of the features. So your turn again, all right, you ready? And these two molecules, my analytical chemists will recognize these pretty quickly. What do you think? Which one has the greater quantum efficiency? Which really is just the greater fluorescence, right? Better ability to fluoresce. Well, again, I hope your eyes zeroed in on this area here where the oxygen bridge is going to lock this group of rings into place. And the name's a giveaway, right? Fluorescein versus phenolphthalein. Fluorescein is really the grandfather of fluorescent species. There's so many derivatizations of this, and it's used in so many assays. So this is a good one to be familiar with. But phenolphthalein, you're probably familiar with from just Gen Chem lab, analytical lab titrations. It's a great chromophore, but because it deactivates with molecular motion, it's not a great fluorophore. So fluorescein it is. Well, what factors affect fluorescence? This is a really important question because one of the greatest advantages of fluorescence is that it's sensitive. So what is it sensitive to? Well, solution conditions for one, solvent, pH, ionic strength, temperature, and especially concentration as well. So that's awesome, right? Fluorescence is a highly sensitive tool, especially to local microenvironments around the fluorophore. Yay, right? We need that. We want things that are sensitive to detect changes in molecular interactions, conformations, behaviors. However, there's always a but, right? But this requires careful experimental controls, right? With great power comes great responsibility. You have to be careful that you control these parameters so that the changes you're seeing are really changes in fluorescence due to whatever perturbation you did, and not just parameters that you did not control. Okay? So since we mentioned concentration, what about concentration effects at low concentration? So for this Beer-Lambert law to apply here, we're at low concentrations, lower absorbances, and you can see, should be familiar, right? Beer's law, there's epsilon BC, that's absorbance. So concentration, increases in concentration are going to produce increases in fluorescence. But we also have this I naught term, right? So the intensity of the excitation light is going to impact the fluorescence intensity. So that's a great thing. So factors that increase fluorescence then, based on that Beer-Lambert equation, is number one, we said the intensity of excitation light, and that's going to be different from UV, right? UV, we send absorption measurements, we send light in, we look at transmitted light, and I send more light in, I get more light out, I take a ratio, right? So I lose that advantage. The molar absorptivity of the fluorophore, if it absorbs photons better, it has a greater chance of emitting as fluorescence. And the concentration of the fluorophore will be important up to a point before other effects take over, which we will look at the end of this talk. So let's do a quick summary. Take-home message 1 for sample and solution considerations. Control of solution parameters, fluorescence selection, sample preparation are really the first important steps in optimizing your fluorescent measurement. So what kind of questions should you ask yourself? Well, you should be aware of what is the quantum yield of the probe? Where does it emit and excite? And does that occur in other areas where there might be background fluorescence? It's critical that you're confident that the observed changes you see in fluorescence are due to experimental parameters that were perturbed. So you need to be sure that you know which parameters in solution need to be controlled and which ones you can be more lax with. How consistent is your sample preparation? Are reagents spectroscopic grade? What's the water quality? I can't tell you how many times folks have come with questions and they're not using 18 megaohm milli-Q water, or they are, but it was stored in a plastic bottle and absorbed the plasticizers. So fluorescence is sensitive, and that's a blessing and a curse. You really have to be careful. All right, so what about instrumentation? Most of you have probably collected an absorption spectrum. I'd be curious to know how many of you have used the fluorometer. Probably fewer than have actually run absorption. So let's work together and look at instrument control by building a simple fluorometer together. All right? So what do we need? Well, I need a sample, right? And we'll work in solutions because that's an easy start. So solution-based, I have a sample cuvette. What do I need now? What we talked about was Beer's law. Beer's law says fluorescence is proportional to the intensity of the excitation light. So I need a light source, right? And it's usually a xenon lamp. It can be continuous or flash lamp. Continuous has the added advantage that it has a significantly greater output. And so, again, remember, more light in, more light out, you get a lot more sensitivity with the continuous sources. So now what? I've got light, I've got sample. Well, I want to choose what wavelengths I send in to excite my sample. I could do that with a filter, right? There are filter-based systems, and it lets a lot more light through. But then I don't have the flexibility of selecting the wavelengths I need. So a monochromator gives me that ability of wavelengths, easy wavelength selection, and the ability to scan the excitation monochromator. Now, if I were just doing a simple UV-Vis experiment, right, just for comparison, if I'm sending light into the sample this way, I'd want my detector on the other side, right? Light in, light out. So I can say incident light, transmitted light, take a ratio, and boom, I've got absorbance. Now, is that a good place to put the detector for fluorescence? No, it's not, right? Because all of the transmitted excitation light is coming through that way. That's not good. And to our advantage is that fluorescence is isotropic, so it's going out in all directions. So a better place to put the detector is going to be at 90 degrees because that's going to minimize any of that scattered excitation light. Well, you can tell we're missing something, right? It's detectors, especially photomultiplier tubes, right? They take a photon of light, they multiply it, it turns it into an electron with a photoelectric effect, and then multiplies it depending on what voltage you set. So, you know, I can go from 1 electron to 1 million electrons and really amplify the signal. That's great. However, these detectors are kind of dumb, right? A photon is a photon is a photon. So what What I really need is an emission monochromator, right? I want to be able to tell the detector and know which photons are coming off so that I can actually know what energy excites a molecule and what energies are coming off when it emits. All right? Looking at this in terms of the output we would get from the detector then, you'll see that we can have for absorbance measurements, we get an absorption spectrum. Tends to be broad and featureless. The absorption spectrum often, but not always, is the same as the excitation. It's not always the same because not all absorption bands result in fluorescence, right? But usually you'll see that absorption and excitation are going to look very similar. The next thing you should observe is that emission, whether it's fluorescence or phosphorescence, is at longer wavelengths than the excitation. This is called the Stokes shift. And so the difference between this lambda max for excitation and lambda max for emission is Stokes shift. In this case, it's fairly narrow. In the case of phosphorescence, which is a much weaker signal, much lower quantum efficiency, we see that the Stokes shift is much greater, right? So that's an advantage of phosphorescence in terms of kind of getting rid of that scattered excitation light problem. Well, let's collect an emission scan, an excitation scan. And a lot of people don't collect excitation scans. You go to the literature, you look up the wavelengths, you enter it, and go from there. It's always good to check. So what we want to do to collect an excitation scan is hold this emission monochromator constant and then scan the excitation monochromator. So I'll sit at a wavelength maximum for emission, and all the light that comes through then is going to show us where this molecule best excites. Okay, that's the excitation scan. For an emission scan, it's just the opposite, right? And you might be more familiar with this if you've done fluorescence. What we're going to do now is fix the excitation at that emission maxima and fix the excitation at the excitation maximum and scan emission. All right, we get this emission spectrum. So what information do we get from an emission spectrum? Well, we learn about molecular structure and fluorescent moieties that are present. We get really important information about the local environment surrounding the molecule being probed. And it's important to note that the shape of the fluorescent spectrum usually is independent of the excitation wavelength. So that if I change that excitation wavelength, I get the same band shape, but simply a greater or lesser intensity. The emission spectrum is often called a mirror image of the excitation one. And here's a nice example with anthracene. Again, our molecular chicken wire, so we have this really nice vibronic band structure with anthracene that you don't see in many molecules. It's not what we would say is broad and featureless, but it's a really nice example of that mirror image rule. So we're okay now with basic fluorescence when we collect a spectrum, but we need to be aware, it's really important that you understand what the scattering artifacts and other phenomenon that can appear in the spectrum. So that way you'll know, is it fluorescence or is it scatter? There are two main types of scatter we're going to talk about today. The first is Rayleigh, and Rayleigh is elastic scattering, which just means that the energy of the scattered light equals the energy of the excitation light that's used. Raman is an inelastic scattering that's due to the solvent and the vibrational modes in the solvent. So the solvent is present in the greatest amount, and even though Raman's a very weak effect, it shows itself and can interfere in fluorescence. It shows up at energies of scattered light that are longer than the energies that are lower but longer wavelengths, right? Let's take a closer look. How do we tell the difference between Rayleigh and Raman? That's pretty easy, I think. Rayleigh can be first or second order scatter, So if the peak we see, the scattered peak, is at the excitation wavelength, it's first order. If we get a band at double the excitation wavelength, that's second order Rayleigh scatter. And it's going to be apparent in most solids and highly scattering solutions, but honestly, you're going to see it in a lot of solutions that you run just because the system is so sensitive. Raman, on the other hand, is going to show up, like we said, at longer wavelengths than the excitation band, right? Okay, so it's easy to identify Rayleigh. Raman's going to be at longer wavelengths, but fluorescence is also at longer wavelengths than excitation, right? It's red shifted from it. So I think a more important question is going to be, how do you tell if it's fluorescence or Raman? And there's been so many cases where I've talked to people and they just didn't realize they were seeing that in solution. A quick qualitative check on this is if the observed peak, you can tell the observed peak is Raman if the peak shifts to longer wavelengths when the excitation wavelength is increased. The peak also appears in the spectrum of the blank. That's another great way to check, right? If it's just the solvent, you know, and you have good clean solvents, and you shouldn't see a fluorescence band, right? So easiest thing to do, run emission scans at different excitation wavelengths for both sample and blank, right? Or at least for the sample. Quantitatively, P chemists love this part, right? We can calculate the Raman band for the solvent at the excitation wavelength used. So for water, it's this equation, and you could use this equation for other solvents by just substituting in the Raman shift constant here for that solvent. Let's take a quick look. If we excite at 300 nanometers and we plug that into the equation, then the Raman band should show up at 335. If I do this at 350, the Raman band will show up at 397. Great. All right, so now, I mean, we can know where these are. So if you want a further confirmation, you can do the quick calculation or look it up online, right? There's calculators. One point to note, though, is notice this is a 50 nanometer shift, whereas that's not what we see here, right? The Raman shift is not going to match this. It's an energy difference. So we're not going to see a 50 nanometer shift here, right? It's slightly less than that. Well, actually, I lied, right? Let me see if I can do the math. Yeah, slightly more than that. So I think what will help us here is let's look at optimizing fluorescence in samples by looking at some example spectra. Let's start with just the blank, right, with just water. So if I excite at 300, like we said, I'll get a scan. This is just a water scan. And this big band here, it's a huge band, notice, at 300 nanometers, right? You tell me, what is it? That's Rayleigh scatter, right? Wherever I excite at is Rayleigh. I should also see a band out where? Out here at 600, second order Rayleigh. This guy is the Raman band, okay? Less in intensity, but still quite prominent. So let's look at a real sample. I happen to have some cranberry juice available on this lockdown, so I created some spectra we can look at. This is diluted, and here you see an emission spectrum of fluorescence versus wavelength, exciting at 365. And several bands should stand out for you, right? 365, 730, 450. So what's going on at this big band? That's just Rayleigh scatter, right? Lambda equals lambda excitation. Out here, another quickie, right? Second order Rayleigh scatter at double excitation. This one, however, what is this, right? It could be fluorescence. It's likely fluorescence, but it could be Raman. And so we need to check it further, right? What are you thinking? What are we going to do to check this? We're going to run the scans at different excitation wavelengths, right? So that's what you see here. I've run the scans at 365, 350, and 320 nanometer excitations. You see them in the colors. So as I decrease the excitation energy. Notice that these bands shift, right? So Rayleigh scatter shifts with that. So does the second order Rayleigh. And we can see this band, well, maybe we need to look a little closer at that one, right? Let's zoom in. So in this case, we notice right away that this large band doesn't shift at all. But what's going on here? I do have other bands which are shifting to shorter wavelengths as I move to shorter excitations. So the band at 450 only changes in intensity, right? So must be fluorescence. The band at shorter wavelengths shifts to shorter wavelengths as I change the excitation. So you know what this is, right? That must be Raman. And one thing that I want you to notice here is that Raman can really get right on top of where you want to look, right? I mean, I wouldn't want to use, colors might be wrong here, sorry, 365 as an excitation wavelength because the Raman band is very close and I might be getting some contribution of that to the signal I'd be measuring at 450. This one at 320 is way better. I've moved the Raman band way off of where I'm looking, so I have confidence in that emission signal that I'm going to see. And I will venture to say that even though going down to 320 increases this, if moving to 320 decreased the fluorescence, it would still be better to use 320 and sacrifice a little fluorescence intensity and move that Raman band away. So now that we kind of know where the fluorophore is, we want to look at what else can we do to optimize the signal, because right now we've really only optimized scatter. We have huge scatter bands and a very small fluorescent band. So this is just a screenshot from the JASCO FP 8000 series software. And you can see that we can adjust excitation and emission wavelengths. That's what we've been doing, right? It's pretty common. Here we can select the mode, whether I want to do excitation or emission scans. Equally or more importantly, excitation and emission bandwidth, right? How much light I let into each of those excitation and emission monochrometers. This is critical, and I don't think enough people adjust this. This is important. You need to determine what resolution you need as well as what sensitivity. And that means changing the detector voltage. So working between spectral bandwidth and detector voltages can give you a nice compromise of resolution that's required and ample sensitivity. So remember the photomultiplier tube, if we adjust that voltage, we can increase the signal that we get. Now, unfortunately, what else increases when I adjust the voltage? Noise, right? So that's why it's a trade-off. We have to work between those two. Also important, because all monochrometers kick out other orders of light, would be an internal filter set. And so, you know, you have control, you can turn them on, you can turn them off. It's nice to use these because we can get rid of some of that second order scatter contributions that may interfere. So let's look at each of these and see what kind of impact it has on spectra. So in this example, I have the same solution that we looked at earlier, except I'm going to try different bandwidths. 10, 5, and 2.5 nanometers show a huge difference in fluorescence signal, right? Kind of hard to see if there's any difference in resolution here, right? Cranberry, the anthocyanins, right, that we're likely seeing in cranberry juice tend, it's very broad featureless spectrum, right? So not a big deal. I think the most important take home here is, wow, I get a lot of intensity by changing the spectral bandwidth. Now, do I need to go to 10 nanometers though? I mean, I am starting to blur in, you can see, I guess, looking at the scatter band, just how much broadening you get going from 2 to 5 to 10. It could be a big deal if you have a narrow Stokes shift, right? So we need to look at detector voltages as well. And I think this is very telling. Here you can see by going from 400 to just 550, not even a huge change, I have increased tenfold the signal that I'm seeing for my sample at 5 nanometer spectral bandwidth. So at 5 nanometer spectral bandwidth, I'm now back up to the intensity I had at 10, but I'm working at 5. So that's a nice compromise. And in fact, you know, given that the detector scale goes from 0 to 1,000 volts, we could easily do this at 2.52 if it was really important. That's another advantage of a continuous lamp, right? It gives so much output that we can keep closing those slits down and still have lots of intensity, lots of light throughput. I wanted to show you this example because it nicely illustrates what happens at different spectral bandwidths for a molecule, right? Molecular chicken wire, Ovalene, that has huge structure, right? And you can see we just lose peaks, right? As we go to these bigger spectral bandwidths. So the larger spectral bandwidth, we're definitely going to sacrifice resolution. You have to decide for yourself how important that is. So increased spectral bandwidth, big decrease in resolution. Now, one thing that I've found over the years a lot of folks don't think much about are these interfiltering effects. So I'm going to close with this and a different look at quantitative fluorescence. So something else for you to consider. Here's a picture of 4 fluorescent solutions. This is actually fluorescein. You tell me which one has the greatest fluorescence. I might be baiting you a bit, right? So let's walk through this. If I plot, just you keep them there and plot right on the cuvette where the fluorescence is versus concentration. I'm pretty low for the one that looks like it's just water, right? Super low concentration. But I get an increase in the next one. But already in the third one, I begin to see the fluorescence decrease. And then in this last one, by golly, it's less than the fluorescence of the most dilute solution, right? So we get this rollover, right? You've seen this in absorbance as well, right? But we get it in fluorescence, and it's due to these interfiltering effects. So concentration effects at high concentrations, then, we recall from this Beer-Lambert equation, which only applies really to low concentrations, we can now look at what factors decrease fluorescence as concentration increases. And number one, self-concentration, right? Self-quenching. So molecules are going to bump into each other because there's so many of them, and it's just going to radiate, non-radiatively deactivate. There's so many molecules around, we could form a new species. We could get dimers or other kinds of aggregation that, again, quench the fluorescence. There could be energy transfer going on, and these interfiltering effects. Let's take a real visual look at these interfiltering effects. So standard cuvette, we're looking at it from the top. You can actually see the band of fluorescence going across here, right? So excitation's coming in from this direction, and we excite across the whole width of the cuvette. And in addition, we're getting emission across the whole width of the cuvette. That's great. That's a typical fluorescence, right? We use we excite all the molecules and we get emission, no interfiltering at all. Well, that's ideal, right? There are 2 types of interfiltering, primary and secondary absorption. So same cuvette view, right? And you might be able to tell it's different, but just to help you out a little, there's the one from before. What's the difference? We have this huge band of light at the front end, so it's so concentrated that all of the molecules that are, in the front here absorb all of the light, and we only see emission from, say, the first couple millimeters of the cuvette. So the excitation light does not penetrate across the full width of the cuvette, and we have a more concentrated solution, but much less fluorescence, right? Because most of the molecules are not excited. This is primary absorption, and I think you should note that it occurs before the emission of a photon of light. So sometimes it's called a pre-filter effect, What about secondary absorption? Well, it's a little more involved diagram, but not a big deal. So in this case, even if we don't have any primary absorption, what happens? The molecule emits, starts traveling to exit the cuvette, and then because of different factors, we see absorption before it makes it out. Some of the shorter emission wavelengths are reabsorbed by the fluorophore itself. So what happens is we have emission signal that's attenuated at those shorter wavelengths, which kind of produces an apparent red shift. Secondary absorption then is going to result from the overlap of excitation and emission for the fluorophore. And I hope you're thinking of that term we talked about, right? What molecules then are going to be more susceptible to these kind of secondary absorption interfiltering? Molecules that have narrow Stokes shift, right? So that's why there's many reasons to choose fluorophores that have a larger Stokes shift. This would certainly be one of them. Even given this, though, really the primary interfiltering that occurs is the primary method, right? That's the one that dominates. This is more minimal. But how do we minimize these? Well, of course, we could use more dilute solutions, right? If we can, but that's something to keep in mind. I mean, fluorescence is sensitive. Take advantage of that and use more dilute solutions and be aware that you're working in the linear range, right? That's just good analytical chemistry. Textbook recommendations, right? Keep absorbance at 0.005 at the maxima for lambda excitation and lambda emission, right? So at those maxima, try to keep that absorbance low. You could try, if you can't control these things, what about a shorter path length cuvette, right? Either on the excitation and or the emission direction. And front face illumination, triangular cells can also be used. So let's close this out with a take-home message, right? Parameters for fluorescence optimization. Hopefully, you realize now that careful compromise of instrument settings are required to get the best signal. We can select wavelengths of excitation and emission, right? Not just use what we see in the literature. Check it out for yourself. Make sure you exclude scatter to maximize the sample signal. Identify and move that Raman band away from peaks of interest. Use filters for excitation and emission channels. There's the internal filter sets can be used to get rid of that second order scatter and also just reduce other stray light. You may need additional external filters if you work at longer wavelengths. PMT detector voltage. People, please make sure that you find that detector voltage that enhances the signal with the least noise. I'm amazed at how many folks just don't play with that much. Do that and you can really get excellent fluorescent data, especially if you work in combination with the slit width spectral bandwidth setting, right? Find that spectral bandwidth that provides the desired combination of signal, resolution, and minimizing noise, right? And working with all these together, I hope you find greater success in your basic fluorescence experiments. Rule of thumb, one more thing, nice little thing to keep in mind is that the sum of the spectral bandwidths for excitation and emission should be less than the Stokes shift of the molecule you're looking at. And that'll help you minimize scattered excitation light in your emission as well. So I want to say thanks for joining us. We're happy to take any questions that you may have. And I hope you find this a valuable resource for your future fluorescence experiments. Thanks.
Thank you, Sherry, for that very, very nice presentation. As Sherry said, we are going to give some minute for you guys to start making your questions. I can see some questions already popping up in the pen. I'm going to let Sherry to take a look of those questions and we can start answering.
Oh, wow, some good questions are coming in. Excellent. Yeah, I'll just start, and we may not get through everything, right? And certainly happy to talk to folks offline as well. The first question I see is, would there be anything wrong with using a larger excitation slit than emission slit? Super excellent question. And I've done this myself. No, it's a great idea, right? If we can let more light in on the front end, right, and know that we're not going to have potentially other fluorescent interferences from that, we can keep it narrower on the emission side and preserve some of that resolution in our spectra. So good question. Let's see, Patrick asked, would surface roughness affect fluorescence? Good question, and you're taking it to a different level, Patrick, in that surface roughness is going to come into play if we look at solids, right? And a lot of what I focused on today was for solutions, but fluorescence of solids, especially with material science today, quantum dots, 2D materials, right? All of that, really important to be able to do good fluorescence with that. And you are absolutely right, Patrick. Fluorescence roughness can affect that because it's going to impact how the light is reflected and scattered off of the sample. So, for instance, you can do solid-based measurements, like on the JASCO. JASCO has a specific fluorometer, the FP8500, for material science work, right? It has a monochromator that has better stray light rejection, and also it just has a lot of design with increased resolution in the red, so that you can look at solid materials and be confident in what you're seeing. And you can measure these with a powder cell holder, a thin film holder. You can use an integrating sphere, right? Another advantage, again, I think I mentioned this earlier, of the continuous source. You can use an integrating sphere with that and be able to look at powders or liquids and measure quantum efficiencies. And in that case, again, the granularity of your sample. If you're looking at a powder, you want reproducible sample preparation so that you have reproducible measurements. All right, let's see. Oh my gosh, so many questions. Separate absorbance. So I have to make the screen, it's very small print. Let's see. How to analyze excitation emission map. Can you give any suggestions on that? I can probably talk a little bit more about that offline, but can say an excitation emission map is really a 3D spectra, right? Where I've taken emission scans at different excitation wavelengths and basically get like a 3D plot. I don't know if my screen is still visible. That's okay, we won't worry about that. But the analysis of 3D fluorescence, you can take slices out of it. You can do other chemometrics on that to look at peak shifts. JASCO actually has a really cool 2D correlation software that we can talk about later that allows you to look at changes in kind of that 3D space. And Carlos, you'll have to let me know when I don't know how long we have for questions. Another important question was about detectors and detector selection. So you may have noticed in looking at instruments that some have different wavelength ranges, right? So there's kind of a standard PMT that is more sensitive in the UV and shorter visible wavelengths. And then there are more red sensitive PMTs that actually go out to like 900 nanometers. And your application is really an important determining factor in which one you use. So for instance, if you're doing fret and looking at more red shifted probes, well, you want a detector, even if you have a detector, say, that goes out to 750, you're like, oh, it goes out to 750 nanometers, and I'm looking at less than that. You want to make sure you have a detector that's sensitive in that range of like 600, 700, and above. And usually it's the more red sensitive ones, the 900 nanometer ones, that are going to give you better performance and better ability at actually detecting those resonant energy transfers. Let's see, what else do we have here? Should we scan emission wavelength from longer than excitation wavelength to avoid too much light going to the detector? Good question. So you're not going to hurt the detector, okay? You should, I think it's really important in any of the experiments, at least your initial optimization experiments, and even when you're checking your sample the next time you run, scan over top of that Rayleigh scatter band. So if you're exciting at 300 and you know your emission's going to be beyond that, start at 290. I usually take the sum of the slits. If I'm exciting at 5.5, I will go down to 290 and look at what that shape of that scatter band is. Let's see. All right. Sorry, trying to shift through these. When I have a high concentration, what is the best way to measure fluorescence? Okay, so yeah, the answer to that question will depend on a couple things, right? If you can, ideally, dilute your sample if you can. And usually the best thing to do is like run UV-vis absorbance first, right? Make sure in like that lower 0.05 or 0.005 absorbance range if you can. And then, you know, I think that'll put you in the right concentration range to not get those interfiltering effects. But also just check, right? Make a concentration curve and see where it curves over so that you know what linear range you can work in. All right. Let's see. Oh, here we go. This is a good question too. Does the software allow for automation of fluorescence scans taken at multiple excitation wavelengths? Good question, Ian. Yes, it does. And there's several ways of doing this. You know, we didn't talk about all the modes of measurement. We mostly looked at just collecting excitation or emission spectra, but you can collect them in a time-based way, right? And set up so that automatically over time, it's collecting, you know, emission scans. If you really just want to figure out, hey, what's going on with fluorescence across, you know, a broad range of excitation wavelengths, our system has the ability to collect these 3D spectra and will let you say you want to, you know, excite from 300 to 350 at 5 nanometer steps and collect emission spectra at each of those. And it gives you the individual spectra as well as the 3D array that you can look at, you know, and be able to analyze. So yes, you can automate that. Just to take that one step further, right? You can do it versus time, versus temperature, versus excitation wavelength, right? We have lots of options for automating that measurement. Let's see. Some other questions here. Oh, a question about sensitivity. So a lot of fluorometers, you know, most vendors are going to list sensitivity for systems, and that how is that done? It's done based on usually the Raman band of water, right? So the Raman band of water is what it is. And so you can use that as a metric for sensitivity by measuring the signal at the Raman band at usually 350 nanometers excitation, and then comparing that to the noise. The kicker is everybody does this differently, right? A lot of people measure the noise off peak, right? Well, the noise off peak is going to be a lot less than the noise on the peak. So, you can get a broad range of numbers. I would say if it's really an important metric for you, run samples and make sure the system can run your samples. Okay, are we doing okay, Carlos, or can I look at?
Yeah, we are about I already got the signal that is it remains like 30 seconds in our session.
Oh, okay. Okay.
Yeah, so still a lot of questions coming up. I just want to say thank you, Sherry. Thank you, everybody, for coming. The questions that we didn't answer in this session, we are going to have a follow-up email trying to answer your questions. Also, we have more webinars coming up for next week. It's going to be circular dichroism with our specialist, Dr. Leah Pendicia. And that's it for today. Thank you very much and have a good day.